in this first section of 8.1 is going to be getting down some basic graphing and some basic information from the equations for exponential growth and decay, and a few application problems to get you started with. And then we'll deal with some of the other things like shifts and stuff like that a little bit more in depth tomorrow. Okay, so we are going to be dealing with this same equation over and over and over. This y equals a times b to the x. We're not going to talk as much today about the a value because that's more of stretches and things like that than we are the b value, which determines whether it's going to be growth or decay. The only thing that kind of helps us know that is going to be these two things. If my b value, the value that I'm taking to the x exponent, that's strange just as it is, but that's where our exponential growth or decay comes from, we're going to have growth. So basically this means when I have exponential growth, that my graph is going to be going up to the right, similar to number 1 down below. At least visually, that's what it would look like. So for instance, if I didn't see the picture for number 1 down here right away, if I just saw the equation, I would take note that the b value, or my base, was 3, and since that value is greater than 1, that's what causes this to be growth. Now, there's one exception where that wouldn't happen, but we're going to get into that a little bit later. Everything else with this, basically you're going to see similar things. Okay? With growth, our function is continuous, so it doesn't have any holes in it. It's 1-to-1, which means I'm not going to have like 2 y values for an x value, or vice versa. And increasing. And again, that's where my up to the right comes from. As I move from left to right, the value of my function increases. Everything else with this is going to be basically the same. Thank you. The domain is going to be the set of all real numbers, which we like to call negative infinity to infinity. Okay, you also can call it all reals. That would be the same thing. The x-axis, there I spit it out, is the asymptote of the graph. Now we haven't talked a lot about asymptotes. Asymptotes are like walls of the function. It's basically you aren't coming through here. So on typical growth functions, what's going to happen is your graph is going to come down to the x-axis and it's going to hug it, but it's not going through it. So we've got to be careful not to get sloppy with something like that and let our graph go through. They're like, oh, that's not there, because I'll get you for that. Okay. The range is the set of all non-zero real numbers, which basically would tell us the range typically with these, unless there's a shift, is going to be from 0 to infinity, because it's going to come down as low as the x-axis, but then it's going to go forever up towards the top. Okay. And then my graph will contain the point 0, 1. That'll be my y-intercept each time. Again, unless there's a shift, because note we're talking about the parent function, okay, the parent graph where we start. The only difference with decay is going to be visually it goes down as we head to the right, like example 2. I start up here, lower, lower, lower. Another example I used earlier in the day was it's sort of like if you go out and you buy a new car. It's got great value at the start. The minute you drive it off the lot, it starts to decrease in value, and over the years, it finally gets to a point where it's kind of like scrap metal. Okay, same type of idea. The function is continuous, 1-to-1 and decreasing. Again, that's what we mean when it's down to the right. It's getting less and less in value. The domain is still the set of all real numbers. So it's still negative infinity to infinity. So you're like, ooh, it's that for every time to the domain? Yes. The x-axis is still the asymptote of the graph. So my wall still is stopping at the x-axis. The range is the set of all positive real numbers. So again, we're into the same type of thing. Now there is one exception on that, but we'll talk about that when we get there. And then the graph contains the point 0, 1. It has the same y-intercept. There's a reason for that too that we're going to explore here in just a little while. But on number 2, same thing. If I didn't see the graph, I'd still be able to tell that this was going to be decay. Because I'd look at my b value and I'd say, ooh, it's 1/2. 1/2 is between 0 and 1. So I know it's decay just from that. And that's what we're looking for here. So sometimes you may just be asked if something's growth or decay, and that's as simple as it can be. But most of our work is going to be done with graphing, where we're looking for specific values and trying to figure out what some of these other characteristics are going to be. So if I scooch this up just a bit, okay, graph each function, classify if it's going to be growth or decay. Now before I even graph these, I should be able to classify if they're growth or decay. Is number 3 going to be growth or decay? Growth. Because, growth. Because my b value is 2. And that also would be my growth rate. So that's really just a fancy way of saying, hey, here's my b value. If it's growth, it's a growth rate. If it's decay, it's a decay rate. So for the rest of these, I'm going to assume that most of you are probably going to be playing with a calculator on this. So I'll clear this out. And again, f of x is just a fancy way of saying y. And if you need a calculator, you can go ahead and grab one. That's fine. I can slow up here for a second. We'll even pause just to make sure. So let's see if this ends up being the growth, that we think it's going to be. Yup, okay. Now again, the simple way is to bring up the chart. Because the chart not only will give me the values that I can put into here so I can graph, but we are going to talk a little bit about where these decimal values are coming from. Because there's a pattern, and it might make it easier for some of you to not even have to bother with the calculator. We all know that 2 to the 3rd power is 8, and 2 squared is 4, and 2 to the 1st power is 2, 2 to the 0 power is 1, and so on. But sometimes it's this part that we forget about. And I wanted to make note of that for you here. So you can be like, oh yeah, that's where that's actually coming from. Okay. Remember, when you have a whole number to a negative exponent, like 2 to the negative 1st, to make it positive, we flip it. We take the reciprocal, which makes it 1 over 2 to the 1st, which is 1/2, which is 0.5. 2 to the negative 2nd, when I flip that down to the denominator, 2 squared is 4. 1/4 equivalent is 0.25. And you see the pattern. It's like, oh. So this is, instead of 2, it's 1 over 2. Instead of 4, it's 1 over 4. Instead of 8, flip it, 0.125 is 1/8. So if you want to just play with the pattern and know, oh, so that's just 1/8, 1/4, 1/2, and go, that's fine. And if you want to stay with the decimals, you can. But I just wanted you to be aware of that. Because I can get the rest of the information from the chart here now. My y-intercept is at 0, 1, not y equals 1. If you write y equals 1, that's a line. We don't want a line. We want an individual point. And speaking of points, I'm going to go ahead, get my points plotted so I can make my graph. If you are going to do this with some other sort of calculator, or you're going to put them in manually because you don't have some access somehow to be able to get hold of a graphing calculator app, again, I would use at least from -2 to 2 as far as my values go to get an accurate idea of what's going on, you always want to use 0 because we're going to be using the y-intercept. And again, remember our asymptote, our wall is here at the x-axis. Don't go through it. You can hug it, you can get close, but it's like that game you used to play when you were younger. You're not going to step over this line. Well, don't you do it. So, but we already know, based on what we had up above, my domain, and again, if it's been a while, remember, domain's my x values from left to right. Well, with all of these, they're going to continuously go to the left, and they're also going to continuously widen and go to the right. My domain is all reals. It's -infinity to infinity, but if you write all reals, that's okay too. My range, my y values, now this is a little different. Remember, range is bottom to top. What's the lowest y value that we're approaching? 0. So my range is going to be from 0, but then it does go upwards forever towards infinity. So that's a little different from some things we may have dealt with before. And then our other favorite, end behavior, you're like, ooh, there's lots of stuff from first semester that's showing up again. Oh yeah, it's going to keep coming. Now, on this first one, I'll do it with words so we can kind of refresh ourselves. We always are going to have one x value approaching positive infinity and one x value approaching negative infinity. And remember, with these, positive infinity for x is to the right. So what I'm basically asking myself on this first one is, and we use f of x instead of y, we're just talking in math lingo here, as my x values go to the right, what's happening to my y values? They're going up, they're getting bigger, they're heading towards positive infinity. Okay, so as x goes right, y goes up or increases in value. Okay? And if you need to write the words down first and then put the infinities to go with it later, that's okay. Because then I do the same thing here. I go, okay, as x approaches negative infinity, or as x goes to the left, what is my y value approaching? Is it going down forever? No, it's hitting a wall. Where's the wall at? 0. As x goes to the left, y approaches 0, or wherever my asymptote happens to be. That's the basics of growth and decay type functions. And whether it's growth or whether it's decay, it all works that same way. So let's see here. 1/2 to the x. Before I graph it, growth or decay? Decay. And again, sometimes that can be tricky because you're like, well, decay, I'd think it'd be negative to go down, but it's not. It's just between 0 and 1. So I have an idea of what this should look like. If you're ever putting in fractions, remember, put them in parentheses. If you don't, you'll get an unpleasant surprise. So let's see if this looks right first before I go to the chart. Down to the right, okay, looking good. Get my chart up here. Now, as you write those numbers in, or once you get those numbers written in, take a quick comparison between the example we just got done with and the one we're doing now. What do you notice that might seem a little odd? They're just flipped. And the reason for that is, if you think about it for a minute, basically all we're doing is the same thing we did in the last one. Because if you think about it, and I'm just going to do one of them here. If I do 1/2 to the negative third, what am I really doing? Well, I'm taking that negative third, I'm distributing it through, and I'm saying, ooh, wait, those are negative exponents. They must flip. And that's where this is coming from. And it's the same down on here. 1 to the third is 1. 2 to the third is 8. It's 1/8. So when you understand the values that are behind it, it makes this make a little more sense on why it occurs the way that it does. So I can go ahead, get those plotted. And again, do not go through that asymptote. Do not go through the wall that is the x-axis. Now, I think a lot of these things now are going to be pretty similar to what we had before. My y-intercept, where my x value equals 0, still 0, 1. My domain, my graph still goes forever to the right, still expands and goes forever to the left. Now, this graph looks different, though. Is my range going to be different? No. Even though the graph looks different, I'm still looking from the bottom, as we approach 0, to the top when we approach infinity. So even though it's decay instead of growth, the domain and range still are no different. Excuse me. But my end behavior may change a little bit. Always write down my x's first, because they're always going to be one of each. So let's see what might change a little bit this time as we do our end behavior. As x goes to the right, as x heads to positive infinity, what's y approaching? 0. So it looks like we might be doing a flip-flop from number 3. As x approaches negative infinity, or goes to the left, y approaches infinity. So basically, we just flipped them. But again, take the time to just look at them, and then it makes life a little bit simpler, okay, with my end behavior. This is something we'll be doing a lot of as we work through these. I'm actually going to jump a little ways in your packet here now for a sec, because some of the shift stuffs I'm going to wait on a little bit. We're actually going to go over to page 2A here, and we're going to look at the models a little bit so we can have an idea as we get into some of the story problems here, what we're going to be dealing with. Okay, so here, with growth and decay, when a real-life quantity increases by a fixed percent each year or some period, it may be a day, an hour, it depends, the amount y of the quantity after t years can be modeled by this equation. Okay, a times 1 plus r to the t, where a is what you start with. That may be money, it may be grams or pounds of something, it can be anything. R is a percentage increase in decimal form, and t is the time in years. 1 plus r is called the growth factor. So you'd actually add whatever that percentage is to it to get that factor. If it decreases, it's the same idea, except you're minusing the rate now instead of adding it. So what we're going to do is we've got a scientist that estimates a specimen began with 730 bacteria. If the specimen grows, increases, by 35% every minute, write an equation that represents the bacteria's growth. Okay, so we always start with A here. What's our initial amount? 730. I'm not quite sure why I put A there, but that's okay. And it says that it grows by 35%. So am I going to have 1 plus or minus the 0.35? Plus. And then again, since we don't have a specific value, we're going to use t. Now I know it mentions here that most of the time that'll be in years. That is interchangeable for whatever problem you're dealing with. In this case, that t can work with minutes. You can leave it written this way, or sometimes, depending on how simple you want to make things, you can literally add the 1 and the growth rate together and put like 1.35. That would be okay. So, how many minutes will pass before the bacteria reaches a population of 9,000? Now, I could play guess and check on this. I really don't want to, though. So this is where I can let the calculator help me again. I can type in my expression, and either one of these will work since they're basically equivalent to each other. And I'll use x instead of t for my exponent. And what I'm going to do is if I look at the chart, I'm going to start scrolling along in the chart. This is one option I have, until I get to where the y value, or my population, would be 9,000. So when it says how many minutes will pass, depending on how you want to read into it, I like to do things where it's a little more specific. If I were rounding, I would have to say at the 9-minute mark, because at 8 minutes I'd still be short. But somewhere between 8 and 9 minutes, my bacteria will have grown from 730 to 9,000, because I get to see how it keeps increasing and increasing. So that's where my application would come in. Okay, but I have to be able to make the expression to be able to get to this, unless I want to do a heck of a lot of guess and check. Ooh, a car. This is the one that I like to do more, so you can see how bad investments these are most of the time. You buy a car for $36,000. Whew. The value y of the car decreases by 14% each year. Write an exponential decay model for the value of the car. Okay. Initial amount, 36,000. Since it decreases and it's decay, I'm going to subtract the 0.14. And again, you can leave it this way. Or if you wanted to subtract it, you could have 36,000 times 0.86 t. That would work too. Estimate the value after 3 years. So again, once I have my expression, and I can type it in either way, I'm going to go ahead and just put it in this way this time. Don't forget that caret or you'll get a flatliner. You'll get the same value for everything. Let's see how much this decreases and how fast it goes. Check that out. Brand new car, $36,000. After 6 years, it's all the way down to $14,000 already. Okay, 3 years. 3 years, it looks like 22,898 we're down to already. It's lost almost a little over $13,000 in value already. Graph the model in your calculator. Already did that. Estimate when the car will have a value of 15,000. And again, you can play this any way you want to. You could round to the nearest year, which you'd say around year 6, or like me, you can want to play. Looks like between years 5 and 6, because at year 5 it's still worth more, but when we get to year 6 and a little closer to year 6, that's when that car will have that value. So I can actually put an application to this. Okay, one last one. So there's one little twist I'm going to throw at you here. So 15, the growth of an antique table's value after 1975 can be represented. So they're giving us the equation this time. What's the value of the table in 1975? I don't know if I even need the calculator for this one. If I punch this in, and go to my table, Now, I'm not going to go to 1975. I mean, we're starting in 1975. If I want to know the value of the table that first year, what value should I use from the table? 0, okay? I need to use the x equals 0 value. It's $325. Basically, I just wipe the growth factor right off of it. Here's the question, though, that I really wanted to go over with you. What is the rate of growth? That's different than the growth factor. Okay, 1.03 is the growth factor. That's not what you're being asked for. What's the rate of growth? The rate of growth is 1 plus whatever the rate is. So it's the 0.03. It's whatever you're adding to the 1. The rate of growth itself is 3%. So be careful. Real close words, totally different types of things that you're looking for. Okay. So here is going to be your job for tonight. If you flip to the back, and I know I normally don't put homework in the note pages, but I miscopied, so I have to apologize. Practice 8.1 will be the first assignment of homework check number 1. There's some application here. Some of them, you're going to go ahead and put up together the expression like we did before. Other times, they're going to make you do a little work, and I'm purposefully not going to give you a little bit of information here on the back. I want you to play with this a little bit and see what you can do. We'll talk some more tomorrow. We'll get you going with some things, but I think a lot of this you're going to be able to do on your own with a little bit of play. So take advantage now. Take some time. Try a few. Okay, I mean, there's only 7 on here, so even if you got 3 or 4 of them even done before you left, some of you might be done, period. But use this, use the notes, try to set up your expressions, and find the values of the answers that we're looking for down there. And then we'll get a little further in depth with this as far as shifts and some other applications tomorrow.